Hey, here we go. Cool. So it looks like we're streaming. I'll just get confirmation that you can hear me if you're there on the stream. So I'm going to just type a little comment, let me know that I'm coming through okay, and then we'll get stuck straight into it. Cool, looks like we're good to go. Alright, so yeah, my name's Jordan. I'm going to be presenting this first half of the MATH2400 workshop. The second half will be on Friday, presented by Gerald. Cool, so we're going to work through today. We're going to work through the first 4 topics. We're going to work through integers and the natural numbers, representation of numbers, modular arithmetic, and we're going to touch on powers and roots, and then the rest of the course will be covered, as I said, on Friday. Cool, this is one of my favorite courses I've taken at UNSW. I really enjoyed it, and I hope you've enjoyed it. So let's go through some of the stuff and yeah, get you guys ready for the exam. Cool, so starting with topic 1, integers and the natural numbers. So we've got this definition here for a commutative ring. Right, so we have rings and we have commutative rings, which have just an extra property. So let R be a non-empty set with addition and multiplication, and this is addition and multiplication in the usual sense. Then R is a commutative ring if the following axioms hold for all ABC in R. So R is this: we've just defined a field, defined a set, a non-empty set. We've given it 2 operations, and then we're saying that these 2 in combination are a ring if the following things are true. So let's skip through and get all these out. So we want to have closure under addition and multiplication. So under both operations we're looking at. We want to have associativity with both operations as well. So as you can see here, associativity in addition and associativity in multiplication. We want to have distributivity with multiplication. So that's just saying here, if you got A multiplied by B plus C, then that is the same as A multiplied by B adding on to A multiplied by C. Commutativity, sorry. So with addition, this is a given, so we need to have that for it to be a ring, and then for it to be a commutative ring, we also want to have the commutativity with the multiplication as well, and then those 2 things make it a commutative ring. So we have the additive identity here as well. So the additive identity is the element of the set that when you add it to another element, you get the same element back. So for this instance, we're talking about 0, and then in the real numbers, I guess. And then we have an additive inverse as well. So what that means is we have the negative numbers. So the number that when you add this element to this element, you get the additive identity, right? And so if we think about it, we can have like 2, we can have -2, we add those together, we get 0. Cool. I wanted to touch down and explain this now because we're going to be using it now and we're going to be using it a bit later on as well. So really just cement that home. Cool. I forgot to say as well, if there are any questions at all at any point, just throw them in the chat. I'm keeping an eye on it, and I'll address any questions. Let me know if I'm going too fast or too slow, or if you prefer if I hammer down into the questions more, or if I stick to the theory part a bit more. Cool. So yeah, let me know. So let's push forward. So we've got a definition of a field. So this is another quick definition we need to touch on. So a field is a commutative ring with multiplicative identity 1, where all non-zero elements have a multiplicative inverse. So we've got this idea of a commutative ring. So we've got this here, and then what we're saying is if you add a multiplicative identity, because we had the additive identity, if you add a multiplicative identity, and then you say if all of these elements in this set have a multiplicative inverse, then you have a field. So you've built this ring into a field. So sometimes you can call a field a commutative ring with identity with the existence of a multiplicative inverse, which is a very long, convoluted sentence. So sometimes we just call it a field. So in order to show that something is a field, we show that it's a commutative ring. Like I said, we show that it has the identity, and we show that every non-zero element has an inverse. And by non-zero, we mean non-additive identity in this case. Cool, so let's get stuck into a question. So this question is taken from the 2018 paper. It just says simply, is Z15 a field? Right, so Z15 we know is the integers modulo 15. So in order to check this, whether this is true or not, we just need to check that last condition. So we're going to check if every non-zero element in Z15 has a multiplicative inverse. So we set up a table with all the elements in Z15, take away the 0. So we've got 1 through to 14. So we can just check this one at a time. So we can say 1. Does 1 have a multiplicative inverse? Well, we look at 1 multiplied by all the other elements of the set that we're considering, and we see that 1's easy because we've got 1 times 1 is 1. So that's quite simple, quite straightforward. Then we can move forward. We can go to 2. So we can say 2 times what is equivalent to 1 modulo 15. Okay, so if we go 2 times 8 is 16, but then modulo 15, that's 1. So therefore 2 has a multiplicative inverse. Then we get to 3, and we see that, well, 3 doesn't have an inverse. And alluding to some stuff later on, we can see that it's because 3 and 15 aren't relatively prime. Their GCD is not 1, their GCD is 3. So again, this is alluding to some stuff we'll touch on later on. But yeah, so we can see 3 doesn't have an inverse, therefore the entire set we're talking about is not a field. Or the set along with the operations is not a field. Because for this to be true, every element has to satisfy this condition. Cool. Let's do another question just to round off this idea. So we're going to do the opposite. We're going to show that Z8 is not a field. So we can take the same approach. We can set up a little table, and this one's kind of handing us the answer here. But you can do the same thing where you can work through all the elements, and you'll see that 2 and 4 don't have inverses, and therefore, because they don't have a multiplicative inverse, then we don't have a field. Again, like I was saying with the 3 and 15 example, you can see that 2, 4, and 8, right? The GCD of 2 and 4 is 2, and the GCD of 4 and 8 is 4, which is not 1. So therefore, they're not relatively prime, and we don't have a field. A little note here. In fact, ZP is a field if and only if P is prime. For example, Z2 is a field, but Z4 is not. Now this goes exactly with this idea that I was just saying. So if we have ZP, right, we're talking about a prime, well, therefore all the numbers in that set of ZP, so they're going to be all the numbers less than P, they're all relatively prime to P, because that's kind of the definition of a prime. Its only factors are 1 in itself. So the GCD of P and all the numbers in that set is 1, therefore all those elements are going to have multiplicative inverses guaranteed. So therefore we'll always have a field. So that's what this is. That's the backbones of what this is saying. An important result, that F be a field, and suppose that A and B are in F. If A times B, or A operation dot B is 0, then either A must be 0 or B must be 0. Right. Cool. So that's that first little part of the topic, and it's alluding to some of the bigger ideas we'll cover later on. So it's really important to grasp these ideas early so that we can use them later. So make sure you ask any questions if you have any. Cool. Let's talk about divisibility. So it says here you've come across divisibility in primary and high school. We're going to make it a bit more rigorous. So it's all the same ideas that you're used to, just doing it in a more definite way. So we let A and B be integers with A not equal to 0. We say that A divides B if there exists an integer k such that B is equal to k times A. So like I said when I talked about the sign, we say that A divides B. So this is something we're already used to, right? So if you think about using the example before, 4 and 8, right? We can say 4 divides 8 because we think about, okay, how many 4s can I put into 8 evenly? And so you go, okay, 4, I can put 2 4s into 8, right? So 4 divides 8, excuse me, and we can also say, going the other way around, 8 divided by 4 is 2. So we're already thinking about this idea of a multiplier, where we're using a multiplier, so 2 and 4 give us 8. Right, so we're kind of used to this idea. Some special properties of divisibility. So the first three are going to be like, are going to stick out to you if you've done discrete maths as well, talking about equivalence relations and all those that kind of area. The one I really want to touch on is the last one, where we're talking about linear combinations. So we can say if A divides B and A divides C, well then A also divides a linear combination of A and B for any integers K and L, right? So we're using an example again, we can think about like, 3. If A is 3, right, we know that 3 divides 6, so how many 3's can we put into 6? We can put 2 3's, and 3 divides 9, we can put 3 3's into 9. So we've got 2 3's and 3 3's. Now if we create a linear combination of those, so if we just add those together, for example, then we get 5 3's. So 3 is still a common factor there. 3 still divides into the product of those two numbers added together. Right, so this is what we're talking about with the linear combination. If A divides this one and A divides this one, the linear combination of them, we still see A divides that. Cool. Going forward, we're going to prove this antisymmetric property. So there's a question here: define what it means to say that for two integers A and B, A divides B, and then going forward from that, prove that if A divides B and B divides A, well then A is just in fact plus minus B. Cool. So I was just having a look at this and stuff coming in the chat. Yeah, so we're saying if this number divides this number and this number divides this number, well, essentially they're the same number up to multiplication by the identity. So going forward, we're gonna start with this definition. So this is a really good place to start off with these divisibility proofs. To start off with this base definition and then work your way from there. So we say that A divides B if there's an integer k such that b is equal to k times a. That's the definition. Now, using this definition, let k and m be integers, so we're doing the same thing the other way around. B is k times a, other way around, a is m times b. So this is two distinct integers, k and m. And these are just coming, so just to be clear, this is coming from here, and then this is coming from here. Cool. Now, so we're going to substitute these. We're going to substitute one expression into the other, right? So we've got this expression for a. Now we're going to put that expression into the first one, and then we get this result. So b is k times m. B is k multiplied by mb, and then using associativity, because that's one of the properties we listed above, we can move things around. So we've got km as our multiplier times by b. So now we've got b on both sides. So let's move it across and let's try and solve for b. So we can see we move it around, we factor it out using distributivity, and then we get this. Cool. So we've got two things multiplied together that equal to 0. And we said before, if we've got two things equal to 0, well then one of them has to be 0. Right? So we'll say that again. Two things multiplied together gives us 0. One of those has to be 0. So we're saying that either b is 0, but that's a trivial case, because if b is 0, then using the definition before, then a is 0, right? And that's a trivial case. It still exists, but it's not as interesting. So let's look forward to, let's say 1 minus km. Let's see what happens if that equals to 0. So if 1 minus km is equal to 0, right, we can move things around, and therefore km is equal to 1. Well, we're talking about integers here, so k and m are integers. So we've got two integers multiplied together that give us 1. Well, the only way that can be true, there's only two cases where that can be true. That's either true if k and m both 1, so it's, where's that? That's case 1 here, right? If they're both 1, then 1 times 1 is 1, that works. Or, alternatively, we can say that they're both minus 1. So you've got minus 1 and minus 1, negatives cancel, it gives you 1. So these are the two cases we're looking at where this is true. But then if we follow these two cases through, well then, if we look at the first case, if they're both 1, we can see that's 1, well then a is equal to b. And then if we look at the second case, if this one's minus 1, and this one's minus 1, then a is equal to the negative of b. Right, so then we've proved that therefore this is true. So if we go down to here, yeah, it says here, which implies that a is equal to plus minus b. So what we did is we start off with the definition of what it means for one number to divide another, and then working our way down, we've found out that, well, there's only 2 cases where this can be true, right? And, well, 3 cases if you include the trivial case, but in the trivial case, 0 is equal to plus minus 0 regardless. So then if we look forward to the 2 more interesting cases, we follow both those through, and then we find in both those cases we get the result we wanted, which is perfect. So therefore we can say it's true. Well, let's try another quick proof one, and then we'll keep pushing forward. Prove that if A divides B and B divides A plus C, then A divides C. Okay, so let's start off with this definition again. Again, this is the best place to start with this kind of stuff. Suppose that A divides B and B divides A plus C. Okay, so then therefore there exists K and M in integers such that we can say that B is K times A, and we can say that A plus C is equal to M times B. Yeah, and again, that's just using the definition, right? So we have these 2 expressions. Perfect. Now, what we're going to do is we're going to substitute this first expression for B into the second expression, and then we're going to rearrange. So we substitute in, we use associativity again. This implies that we can move the A over because there's nothing multiplying outside these brackets here, nothing outside there, so we can just, I don't want it to get confused that we're talking about absolute value. Yeah, cool. So we can just move the A over. Great. And then we find an expression between C and A. Cool. So again, we're talking about integers here. All right. So we're talking about integers, M and K, and integers here. So then if we get an integer times an integer, subtract an integer, we get an integer result. Right, so this expression here, right, this is still an integer. So therefore, we're saying that C is equal to some integer times A. So let's call this integer. Let's say that, let's let Z equal to MK minus 1. So therefore, C is equal to Z times by A. Well, that's, by definition, that means that A divides C, because that's what we're using that definition from before. So looking at this expression, we say that this must be an integer, therefore A divides C. And we've proven the result we're looking for. Cool. Again, at any point, if I'm going too fast or you want me to touch on something again, just let me know. Otherwise, I'll just keep pushing through this stuff so we can get through as much as we can. Cool. Let's talk about the greatest common divisor. So now, suppose that D divides both A and B. We say that D is the greatest common divisor of A and B if and only if C is less than or equal to D for all C where C divides A and C divides B. Okay, so greatest common divisor. So there's 3 words here, and they all contribute in some way. So we've got divisor, so we're saying that this number divides, well, we're saying it divides both A and B, divides these 2 other numbers. Common, so it's common between the 2 of them, and greatest. So we mean that this is the largest one. That's all that's saying. It's saying that if you find another divisor out there in the wild, if you're searching for all these divisors and you find another one, it's got to be smaller in magnitude than this one that we're looking at, D, over here. Cool. So that's all that means. Interestingly, if this is something that has sparked intrigue in you, I definitely recommend doing MATH2400, or just going out and researching this yourself, like looking on Google and looking through stuff like that, because this is something that you can also apply to a whole bunch of other fields, not just the ones that we're used to. And it's really interesting because it works pretty much the same as you work through it, but it's really cool to see it applied in other contexts. There are some things you need to be a bit careful about, but it works kind of the same. So, in other words, D is the GCD of A and B only when D divides A and B, so it's a common divisor, and if C divides A and C divides B, then C is less than or equal to D. So it's saying if there's another one, it's smaller. Great, let's do a question. So, from the 2016 paper, it says, let M be the product of all primes between 10 and 20, and let N be the product of all integers between 30 and 40 inclusive. And then find the GCD of M and N. Great, so let's set up a little fraction here. So we have all the integers between 30 and 40 inclusive. So I just want to make it clear that this is not a subtraction. So we've got this set here, and then we've got all the primes between 10 and 20, right? And we're trying to find the greatest common divisor. So we're trying to find the biggest number at the bottom here that's going to divide into this top number cleanly, and so we're going to get like an integer result at the end. Okay, well, let's think about this. Well, we've got all the primes between 10 and 20, so if we list all the primes, we've got 11, there's 13 in there, 14, 15, 16, we've got 17, we've got 19. So these are all the primes. And so I guess the greatest common divisor, so we're talking about the product here, the greatest common divisor, I guess, would be the product of as many as possible. That would be the biggest one. So we want to see if we can find that all of these numbers divide cleanly into this numerator here. And if we can't find that all of them do, we'll at least as many as possible. So let's go forward and see how that goes. So we shall find all the primes between 10 and 20 that appear in the prime factorization of integers from 30 to 40. Cool. So we see that 11's in there, because we've got 11 times 3, which is 33. Cool, that's good. 13's in there. Great, that's good. And again, times 3, we get 39. 17's in there too, with 34, 17 times 2. And then, so I guess the last one to check is 19. So we check 19, and 19 times 2 is 38. So therefore, all of these numbers appear. So if we just go back to this drawing, so this is the biggest this set can be, right? So I guess the biggest number we could make is, whoops, that's very messy, I apologize. That's the biggest number we can make on the bottom, and we're saying, well, all of these divide into it, so therefore the greatest common divisor is the product of all these numbers. Cool. Moving forward to 2017 question. So it says, find the greatest common divisor of the GCD of 6 to the 5 and 15 to the 3. Cool. So let's go through this. So tip, find the prime factorization of both numbers. So again, we're trying to find the biggest number we can that divides cleanly into 6 to the 5 and 15 to the 3. So a useful way to do this is to look at the prime factorization. So we see that 6 is 2 times 3, and then if we raise it to the power, we then get 6 to the 5 is equal to this. And then we do a similar thing for 15 to the 3, and we get this. Cool. So we have a look at what's in common. So we can see that the 2 and the 5 aren't common, so they're not going to be greatest common divisor at all. But we see there's a 3 in both. Okay, so we've got the common divisor. Now what's the biggest one we can make? Well, we see that in 6 to the 5, we've got a 3 to the power of 5 term, but we've only got a 3 to the power of 3 term over here. So therefore, the biggest number that we can divide cleanly into both numbers, because it has to be both, is therefore 3 to the 3. So that's our limit. So then the greatest common divisor is the number that's common to both factorizations, hence the GCD is here, and we can expand that out and call that 27. Cool, so the basic approach for this kind of question is just find the prime factorization, and that's going to really help. Cool, let's keep pushing forward. So, like I alluded to before, two integers m and n are said to be relatively prime if their GCD is 1. Okay, so let's think about this for a second. The GCD is 1. So if we think about two prime numbers, let's say 7 and 11, right? So what are the factors of 7? Well, 7's a prime number, so it's just 7 and 1. And 11's a prime number, so 11 and 1. So there's no common factors between the two of them other than 1. Okay, so those are relatively prime numbers, but they're also prime in and of themselves. So let's think about 7 and 8. So 8's not a prime number, 8's a composite number. So 7 and 1 divide into 7. We have 1, 2, 4, and 8 divided into 8. Well, again, the only one that's common there is 1. So the GCD there is 1, right? And then we can look at two composite numbers, even 8 and 9. So you got 1, 2, 4, 8 for 8. You got 1, 3, 9 for 9. Again, the only thing common is 1. So it's building on this idea of primality. You can say that two things are relatively prime to each other if the GCD is 1 and they don't have any common factors between them. Cool. So we're going to look at this question. Show that this crazy number here and this crazy number here, show that they're relatively prime. Okay, so the way we're going to do this is we look at so it says tip, look at the prime factorization of the left number and make a contradiction argument. So something that's useful sometimes is to proof by contradiction. So it's saying that show that this thing is true. Well, you're going to say, well, actually, I'm going to try and show that it's false. And then when I show that it's false, I'm going to reach a contradiction. And then, therefore, the assumption I made that it was false was incorrect. Must be true. So let's look at the prime factorization of this left number, like we did for the previous question. So suppose they're not relatively prime. So if we look at the prime factorization here, we expand it out. We get 3 prime factors raised to these different powers. And for this question, the powers don't really matter to us. We don't really care like how big the number is right now. We just want to see, are these primes in both numbers? And then if they are, we can look at the powers and see how big of a number we can generate. But first of all, let's just look, can we find these prime numbers that generate this number in this other number as well? Cool. So it says here, at least one of 2, 3, or 7 has to appear. So we mentioned when we were talking about, we were motivating this before, 7 is just 7 and 1. 7 times 1. That's the only prime factor. Well, that's the only factors we can talk about. This one's not a prime. And we can see that 7 is clearly not a factor of this number here. There's no 7 in there. The 12 has 2s and 3s. The 15 has 3s and 5s, and the 11 just has 11. So there's no 7 in there. So if A divides this whole number, it has to divide both parts of it. So this is that linear combination thing we talked about before. So if A is gonna divide what can we call it, B plus C, right? A's got to divide B, and A's got to divide B. We've got to have both conditions are true. Cool. So moving forward. So actually, before we move forward, so what we're doing here, just to be clear, is we're going to say let's test out all these numbers we found. We found that these numbers have to appear in the number on the right. Okay, so if they appear in the number on the right, they have to divide both parts of that number on the right. They have to divide this part and this part. So there's only 3 prime numbers here. Let's check them one by one, and let's create this proof by contradiction. So let's see, does 2 divide this number here? Well, it does divide this part, but it doesn't divide 7. So therefore, cancel out the whole number. We say it does not divide. Same with 3. 3 divides into here. Actually, it divides in there quite a lot, but it doesn't divide into this part. So therefore, 3 does not divide this whole number. 7 definitely divides into here, but going the other way, it doesn't divide into this side. So then 7 doesn't divide either. So we've checked all the cases. So none of these prime factors appear in the prime factorization of this number on the right. Therefore, no combination of powers of these numbers can appear in the factorization either. So we've checked all the possible, so we've looked at all the primes that make up this number on the left, and we've said that if any one of these appears in this number on the right at all, then the GCD is going to be that number. But we found that none of these do, so therefore the greatest common divisor must be 1. And then we've shown, just answering the question, we've shown that they're relatively prime, because by definition that means that the GCD is 1. Cool. Alright. Euclidean Algorithm. Really powerful tool. Really simple, but you can do a lot with it. Very powerful. So the Euclidean algorithm is a simple algorithm to find the greatest common divisor of 2 integers. It says here you don't need to know the ins and outs of the algorithm, just how to use it. If you are interested in the ins and outs of it, definitely would recommend delving deeper into it. Like I talked about with this GCD idea, this is something you can actually extend to a whole bunch of other fields, and it's really interesting how it happens. Quite cool, actually. So the general strategy of using this algorithm is you write the biggest number as a quotient of the smaller number. So you got two numbers, right? The bigger number as a quotient of the smaller, and plus the remainder. Then you repeat this process by writing that smaller number as a quotient of the original remainder plus the new remainder, and you keep going. And if you're thinking about like coding this up, like if you're writing a program, for example, our end condition is we keep going until the remainder is 0. That's our end condition. That's when we want to stop. Cool. So let's work through, let's touch on this and then we'll work through an example. So Bezout's identity, I say Bezout, I might be pronouncing that incorrectly. So Bezout's identity, so that's what you do when you go down the Euclidean algorithm, right? When you come back up, that's the identity you've got. So you work down until you get to 0, that's your end condition, you stop. Then you substitute all those expressions back into each other and you get a final expression known as Bezout's identity. So let m and n be integers, not both 0, and let x and y be in Z. Then the GCD of m and n is a linear combination mx plus ny. And note, however, if c is equal to mx plus ny, c is not necessarily the GCD. So if you're just stumbling out in the wild, again, I don't know why you're out in the wild so much, but if you're stumbling out in the wild and you come across an expression that says c is mx plus ny, you can't guarantee that c is the GCD, because there could be a sneaky factor hiding in these numbers where it's actually something a bit like this. There could be a sneaky factor hiding in there that you don't know about, because you don't know how that expression came about. So if you're using the Euclidean algorithm, you can guarantee this though. Cool. Just a quick definition about a prime number. So a prime number is any prime p greater than 1 that is divisible by 1 in itself. So it has two factors exactly. We don't typically declare 1 to be a prime number. So sometimes people get confused. Is 1 a prime? Is not a prime? We're just saying clearly out loud now, 1 is not a prime for our purposes for this course, at least. I think most people consider that to be the case, but at least for this course, that's what we're going to say. So strategies for questions regarding prime numbers. So a good strategy is to remember that the only even prime is p equals to 2. Every other prime is odd. That's a really good strategy. It helps when you're checking cases of things. And for p greater than 3, so not greater than or equal to, for p greater than 3, p is congruent to 1 or 5 in mod 6. Cool. And we touched on the fundamental theorem of arithmetic in a second. But just quickly jotting it down, any positive integer is a unique up to reordering factorization of powers of primes. So you get any number out there. This kind of blew my mind when I first saw this. Any number, any positive integer, sorry, I should be more specific. Any positive integer, you can create a unique factorization of powers of primes. And we've already seen this. We've been doing this in the past with questions. We understand this idea. Cool. This is a good definition of prime. Again, if you do Math2500, you'll see this. Like, you can apply this to then other fields as well. For primes p and integers ab, if p divides ab, then either p divides a or p divides b. That's how we define it. And if you think about it, like let's take a prime 7, right? And then if we're talking about 42, right? So we can say that 42 is equal to 14 times 3. So 7 doesn't divide 3, but it does divide 14. That's what we're talking about there. Cool. So let's do this question, and I think maybe this might be the last question we have time for this this chapter, but we might push forward into the next one in a second, just so we get everything covered. Cool. I was just checking the chat real quick. So this question here, find all prime numbers p such that p plus 17 is also a prime number. Great. Okay, so I'm going to use a couple of things that we talked about before. So there's method 1 that I'm going to run through with you guys. There's also a secondary method here that uses one of the properties we listed before. The slides are going to be available afterwards. So have a look through that, or try and come up with it on your own and see if you can figure out how to use this to create this proof. So we're looking at method 1. So, okay, find all prime numbers p, such that p plus 17 is also a prime number. So if p is a prime, then P is greater than or equal to 2. That's guaranteed. P is greater than or equal to 2, because the smallest prime number we can ever think of is 2. Importantly, P plus 17 is then greater than 3. It's much greater than 3, because it's greater than or equal to 19 by definition. So P plus 17 is greater than 3. Cool. So we're saying we're gonna assume that P is a prime. We're gonna start there. We're gonna say if we've got this number P, okay, let's see if let's call it a prime, and let's see how can we make it that P plus 17 is also a prime. Is that possible? And if it is possible, what is that prime? So P is a prime, P is greater than or equal to 2. If P plus 17 is also a prime, it has to be an odd prime, because the only even one is 2, right? So P plus 17 is greater than 3, so if it's a prime, it's an odd prime. Okay, note that P plus 17 is only odd if P is even. Okay, so let's think about this for a second. If we get some odd number, right? And then we get another odd number. Sorry, I did that wrong. If we add those two odd numbers together, right, we get this plus this equals, right? But this is an even number. This is an integer. So odd and odd gives us even. So if we want P plus 17 to be odd, P's got to be even. Okay, so let's put these facts together. Well, so okay, P is a prime, P is greater than or equal to 2. Okay, so we know that. If we want P plus 17 to also be prime, it's got to be an odd prime. But if it's got to be odd, P has to be even. Well then, P's got to be 2. So P equal to 2 is the only even prime possible. That's what this says here. The only even prime is P equals 2. So therefore, find all primes P such that P plus 17 is also a prime number. The answer to this question is the set containing the number 2. Cool. That might be. There's a couple of ideas playing around this. That might be a bit tricky. So yeah. So just let me know if you want me to go over this again. Explain anything. I see someone said they hated this question. I apologize if I'm bringing up any hard memories for you. So this is method 2, so you can have a look through it later, or you can have a go at constructing it yourself. Cool. We talked about this before. The fundamental theorem of arithmetic is really important. You can also extend this to the negative integers by adding -1 into the product. Cool. Ooh, harder question. 2 exclamation points must be hard. Okay, here we go. What is the GCD of this number for an integer n? So the way we're going to do this is we're going to essentially break it down into a product of GCDs. All right, so we're going to try and consider each part of this one at a time, and we're going to use this property that you can have. Hopefully you guys are familiar with this. You can use this property, right? So you've got GCD of 2 numbers. That's the same as the GCD of that first number, or you can do it the other way around as well. But one of those numbers, and then those 2 numbers added or subtracted. Yeah, cool. So we're going to use that property. So we break it down. So this is what we're going to try and show. This is what we're going to work towards. So first one, 2 is even and prime, right? And this is an odd number, guaranteed to be an odd number. So no odd number can divide 2, so therefore the GCD is 1. You've got an odd and even number, guaranteed to be GCD 1. Oops. Cool. Then looking at the second part, so we're using this property up above. The GCD of these 2 numbers, you subtract one of them from the other side. Now you've got 2 numbers that are consecutive. Well, you think about 2 and 3, you think about 4 and 5, you think about 10 and 11. Their GCDs are all 1. 2 consecutive numbers, the GCD will be 1. So we've got this second one listed down. The third one, I'm going to attack it the exact same way. So we get this right-hand one, subtract it from the left-hand side, then we get 2 consecutive numbers again, which is 1. Right, so then we're breaking it down into this product, and then we're saying that therefore the GCD of this entire thing must be 1. Cool. I worked through that one a little bit quickly, but I think it's touching on this base idea and just using it a bunch of different ways. And I want to make sure we get to a bunch of other stuff. So yeah. So let me know if you want me to come back to this at all. Cool. Beautiful. All right, let's get into chapter 2. That's a huge prank. Easy question. Masquerading is a hard one. Yeah, it's a classic Igor thing to do. Okay, base B representation. So we think of like the numbers we're used to in everyday life. They're usually represented in decimal in base 10. But you can actually represent numbers in any base, and computers do this, representing in base 2 in binary. There's a lot of things use hexadecimal as well. Base 6. No, is that right? No, there'd be hexadecimal, base 16 or something. Yeah, base 16. But yeah, so we use different bases all the time. So we're just kind of defining this rigorously, and we're going to work through some stuff here. Cool. So this is the basic algorithm. Yeah, so I think this is best explained with a question. So let's maybe look forward to, yeah, so this is all going to be in the notes if you want to look through it. But I think the best way to do this is let's go to a question and let's work through this. So we're going to try and write a third in base 2. Okay, so let's have a look at this. Applying the Euclidean algorithm, right? So we see that finding the highest, finding the highest powers of 2 smaller than the remainder. Okay, so what we're going to do is if we think about the number 7, right? So the number 7, we write it in base 10. We go, okay, like what's the biggest power of 10 that I can put into this? Well, I can't put 10 to the 1 because that's bigger. But I can put 10 to the 0. So I've got 7 times 10 to the 0. Right, so we're using this idea, but we're looking at fractions. So we're saying like, okay, well, what's a power of 2 that's smaller than a third that I can squeeze into there? Okay, so we think, well, half, that's equal to 0.5, so this is equal to, we've got 3's all the way down. So that's too big. So we'll look at the next one. So we can say, look at 1/4 or 1 over 2 squared, which is 0.25. So okay, that works. Okay, and then we've got some change. So we've got 1/4 and some change. Okay, that's working. So let's try to break this down further. So we've got 1/4, and then we break down a 12th into a third times 1/4. Now we look at this. We go, hold on a second. What's going on here? We've got a third again. We just started with third. Well, this is a hint to you that this is going to be recursive. Maybe recursive isn't the right word. It's going to be repeating this expansion. Because if we try and break down a third, we're going to break it down into this again, right? And see we're going to be jumping by 2 powers each time. And it's going to be repeating ourselves. So it's going to have, I think the term is reciprocity order 2. I think that's the technical way of saying it. So what's this saying here? This means that we'll have the same procedure with the same number of every digit. We shifted by 2 to the right. Exactly, that's what we're saying here. So we can see that a third is equal to 1 times. Actually, let me do it a bit more rigorously. Sorry, this takes forever to rub out. I don't know how to fix that. It's something I should look into over the break. So we've got 0 of these, and we've got 1 of these, and this pattern's going to repeat. We're going to have the 0 and the 1 repeating. So we've got 0.01, and this is repeating. That's how we do that. Cool. We're going to do some more questions. Let's keep going forward. Let's look at this one. So we're going to write 7 2/3 in base 4. So the approach is we look at the integer, then we look at the fractional part. So luckily we used 7 before. I think maybe it popped into my head because I knew this was coming. So we can break 7 up quite easily. We're looking at base 4 this time. So what's the biggest power of 4 we can put into 7? Okay, so we think we just pick one at random. 16, no, 4 works. So you can put 1 4 in, and then what do we got left? We've got 3 times 1, which is 4 to the power of 0. Anything to the power of 0 is 1. Great. So we've split up 7 into powers of 4. So therefore, this is our representation here, 1, 3. So yeah, it's not necessarily correct to call it 13 because it's the connotation that we have of that is we're talking about decimal base 10, but it's 1, 3 base 4. You can say something like that. For the fractional part, we find the biggest power of 4 smaller than 2/3. So the same approach as before. So luckily, the first power we look at, right, is, so if we're talking about integers, right, we're looking at 4 to the power 0 and 0 upwards. And then when we're talking about, we don't start from 0. We talk, because 4 to the 0 is 1, which is still an integer. So we always start from -1, or we're talking in fraction. That's where we start. If we're talking about base 4, of course, it would be arbitrary base b. So 2/3 is, we can put 2 quarters in there, so that's a half, and that's still less. That's good. We've got 2 quarters in there, and we've got some change again, right? And then we split up the change, and we go, okay. So we notice that a sixth is a quarter times 2/3. Well, hold on a second. We've just done the same thing again, right? We've found 2/3 in there. We're going to be repeating. So we've repeated this time. We've got the first power, and then we repeat it on the next one. So it's going to repeat every digit, right? Because we've got 4 to the power, 4 to the power of -1, which is the first one. And then we've gone to the next one, and we're already repeating. So that's going to repeat there, and we're just going to keep repeating all the way down. So this one's going to be quite simple, actually. It's going to be this multiplier here, repeated. And the reason it's 0 is because we're just talking about the fractional part right here. We're just talking about this fractional part. So it's 0.2 repeated all the way down. So we've got the integer and the fractional part. We put them together. There we go. That's how we represent this number in base 4. Now you might be asking to yourself, well, it's quite convenient that we keep hitting this. We keep hitting this condition where we're going to repeat all the time. Where's this? Is there a note here? Maybe we'll get to it in a second. If you don't find that is happening, like if you don't recognize that, because it takes a second to figure that out. You don't recognize that, it's okay. You just keep working through this. You just keep doing your expansion, and you're going to find that you're just going to get 2, 2, 2, 2, and you're just going to keep seeing that, and then hopefully it'll click at some point. Okay, this is repeating for some reason. Why is this repeating? And then you'll start to pick that up. So if you don't pick it up straight away, that's okay. It'll become evident hopefully after a few iterations. It's just if you do pick it up, it's a lot quicker, because then you can just stop and write the expansion, because you know exactly how the rest of it is going to play out. Cool. I'm just thinking in terms of time. What have we got? We got this question. Yeah, okay. Yeah, cool. I'm going to leave this one because it's using the same ideas we're talking about here in reverse. And I want to make sure we touch on this and continue fractions quickly before we run out of time for this section. Cool. So converting to and from base m squared. So there's a cool little trick we can use for converting between base m and base m squared. So it says here, general strategy. So this is if we're going from m to m squared. You group the digits in blocks of 2 from right to left. You convert those into m squared. So how does this come about? Well, we're talking about if you've got your arbitrary expansion, you've got a1 or a0, b0. You've got a1, b1. You've got some arbitrary expansion here. So you're combining the powers 2 at a time. So you're combining these, right? And you're bringing them together, and you're considering them. Yeah, considering them 2 at a time. And then when we go the other way, what we do is we get one number and we split it into 2 blocks, and we're coming back the other way. So this is, again, best explained with a question. So let's work through this here. So writing 153 in base 3, so this is the easy part, and then we'll do the secondary part, which is then going from base 3 to base 9. So we find the biggest power of 3 we can fit into 153, and this might take a second to figure out, so you have to think for a few minutes, and then you go, okay, 3 to the power 4 is the biggest one I can fit in there, and some change. So we've got this on the end here, right? And then you can split this out all in one equation if you want to, and just already have it in your expression, or you can use like the Euclidean algorithm and work down. up to u. Yeah, it's like Euclidean algorithm adjacent. It's not the exact same thing. So you work your way down, and then you hit your end condition, and you stop. And you go, okay, let me rewrite this. Let's substitute back into sub 18 back in here, sub 2 back into there. And then you get this expression. So you got 1 times this, 2 times this, okay. And then you've got 0 times 3 to the 1. I think that accounts for, oh, sorry, and 0 times 3 to 0. And that accounts for pretty much everything. So then you just read them off. You got 1, 2, 2, 1, 0, 0, and that's it. 1, 2, 2, 0, 0. Great. So now we're going to block it into group 2. So we've got group 2, group 2. This one looks awfully lonely, so we put a 0 in there. So it's got a buddy. So it's done it here for us. So we block it into groups of 2. Converting 0 is quite easy because 0 is 0. It's just going to map over pretty well. Excuse me. So it maps over pretty well. So we've got 0. Then the next block. So okay. So we think going 2 2 in base 3 to base 9. Okay. So 2 2. Okay. So then I think about, okay. So if I can fit going from base 3. Yeah. Sorry. Let me rub this out. I made a little error. Yes, sorry. So you got 2 times 3 to the 1 plus 2 times 3 to the 0. So that's what this is saying here, right? And then okay, so let's have a look at this. Let's go, so that's 6 plus 2 is 8. Right, well that works in base 9, so there we go. And we can do a similar thing here, but this one's quite easy, it's just 1. So you've got 0 times 3 to the 1, which is 0, plus 1 times 3 to the 0, which is 1. So you got 1 here. So we bring these together, you got 1, 8, 0. Now a nice little check that you can use when you're looking at this is if the base that you're changing between is getting smaller in magnitude, then the expansion should get larger. Not necessarily magnitude, because it's technically the same number, but your expansion should get larger. So we can see this here, like 153 goes to 180, and it goes to this in base 3. So it's a good little check just to make sure you're doing the right thing and going the right direction. You can go back the other way as well, so it's the exact same thing. So I'll leave it up to you guys to have a look at that. All you're doing is instead of expanding the blocks, instead of expanding the blocks, what am I trying to say? No, sorry, instead of compressing the blocks, you are expanding the blocks. Yeah, so 0 maps over 0 again, and works the exact same way. Cool. I want to make sure we have a look at, great. Perfect, okay, great. Let's just quickly touch on this really quick. Base 2 representation on GCD and binary. So these are some little tricks for you when you're using the GCD when you're working in binary. So just quickly reading these off just to remind you guys. Let m and n be positive integers in base 2. If m and n are both even, then the GCD of m and n is equal to 2 times the GCD of half those numbers. If m and n are both odd, with m greater than n, just making that choice, then the GCD is equal to the GCD of m minus n and n. Right, and that's tied to that idea we talked about before, where you can use this linear combination. Linear combination? Yeah, linear combination. If one of m and n is even, let's just assume m is, let's just make a choice, then the GCD of m and n is equal to the GCD of half m and n. Right, this makes sense, because if you've got, if you've got an even and an odd number, the even factor is definitely not going to be an odd number, so you can just take that out, and you've got the same GCD. So these rules are just they're just using certain properties to just get rid of the things that are obvious. Well, if we know this thing, well then obviously this isn't a factor in those things, so we take it out, right? So if they're both even, right, then you can take the 2 out the front and look at half that number, because you know that the 2 is going to be in the GCD, right? But there's other stuff to work with in there. So it's just helping you, it's helping you churn through these GCDs a lot quicker. And the last one, if m equals m, and GCD of m is m. Well, yeah, if we're talking about, if we say, what's the GCD of 7 and 7? I must love 7 today, I don't know why. That's 7. Yeah, cool. All right, continued fractions. So let's have a look at this. Some notes on continued fractions. Yeah, if a continued fraction terminates, then it's rational. That's the definition. If the continued fraction is periodic, then it is irrational. Let's talk about the mapping between the continued fractions and the number. So we denote the period by bar at the top. We've been using this already. And denote that the continued fraction is periodic by A2 and A3. Yeah, cool. Excuse me. There should be a note here. Does it say it here? Yeah, it's coming up in a second. So, yeah. So what we're going to do is we're going to try a couple of questions. There's two different approaches. So if you've got a continued fraction and you're trying to find the number, what you want to do is you want to, yeah, cool. If you've got a continued fraction and you're trying to find what the number is, a good thing to do is then you just work through the fraction, flipping, adding, flipping, adding. You just go that way. If you've got the number and you're trying to do a continued fraction, it's the reverse of that. It's a bit tricky to get your head around, but we're going to work through it. It says here, if n is periodic, start by solving the periodic part, and then recombine for the final answer. So we'll see that again in a second. So again, this is the algorithm. I think it's best explained with a question. So this question here is from the 2016 past paper. Define the golden ratio and find its continued fraction expansion. So this is the golden ratio here. Absolutely beautiful piece of mathematics right there. We begin to find the continued fraction representation. Okay, cool. So let's work through this algorithm. Here we go. So first part, you find the integer part of the number you're looking at. So you take the floor function, find the integer part. So the integer part of this is 1. Right, and we can check that calculator by calculator, or just have a look and figure that out for ourselves. We find that the integer part is 1. Now what we want to do is we want to find the remainder. So we get the actual number and we take away its integer part, and we get some remainder. So once we do this, we get this. We're going to leave it in insert form just to play around with it for a bit, because we'll see that it's helpful for us. So the next step is, what you want to do is you want to flip that remainder. And this is how we get this continued fraction, is because you've got you've got a fraction, and then you've got a number added, and you've got another fraction, and you've got a number here, and it adds to another fraction. And this is how we do this. So we're subtracting and flipping, because later on what you do to come back is you flip and then add. So it's the reverse process. So we've got the integer part, we find the remainder, we flip it, we find the integer part, find the remainder again. But we don't need to keep going, because we noticed that when we flipped it, we just got back to where we started. So this is the same when we were talking about base B representation. This is where we started, so it's gonna give us the same process going forward from this. Right, okay, so we noticed we got an integer 1, and then we repeated straight away. We didn't get to find another digit, so therefore this 1 is gonna repeat. So we go, the way we write this is we write 1 semicolon 1 repeated. So okay, so 1, because we're talking about the integer part of the number, and then beyond that we're now talking about the fractional part of the number. And so maybe I misspoke when I kept talking about finding the integer part. Yeah, it's about, well, no, you are finding the integer part, but the integer part of the original number is when we do this first step. So that's our 1 here. We've done that. So now any other digits we find, enter into the fractional part. So we write it as 1, and this 1 is going to repeat, because like we said before, we're just going to do the same process and repeat. And like I said before, if you don't recognize this straight away, it's okay. Just work through the algorithm a few steps, and then you'll start to see a pattern emerging, and then hopefully that'll spark the idea that it's repeating. Cool. Let's try another one to just get our heads wrapped around this. So expand 147 on 32 into a continued fraction. Okay, so step 1, find the integer part of this number. Okay, so we take the floor of that, and we find that's 4. Okay, great, so we've got 4 here. Now we find the remainder, so we subtract 4 from the original number, and we get this. And this is something that's less than 1. So the flipping is because we want to get something that's greater than 1, so we can find this digit by taking the floor of it again. So we find that this is the remainder, we flip it, we take the floor, we get our next digit, we got 1. So we got 4, which is our first part before the semicolon, and now we're into the fractional part, so we've got a 1. Okay, so let's keep going. So we find the remainder, we flip it, we take the floor, we get another digit, great, we're powering through this. We find the remainder, we flip it, we take the floor, we get another integer, great. Now we get into this last step, we find the remainder, but we see something interesting, we see a 1 on the top. Now this might not be obvious straight away, but when we flip that, we get a whole number, we get an integer. So therefore we can't continue, because what we've done is, well, what would happen on the next step is we'd go, okay, let's find the remainder. So we go 6 minus 6, well that's 0. So that's our end condition, because we can't keep going from there. So this is the last one, so we flip that and we get our last digit as 6. Right, so we started off here with the first part, then everything after that semicolon, right? And we can see here, so we got 4, semicolon, and then we got a 1, we got a 1, we got a 2, we got a 6. And at no point in there did it repeat, it just terminated. So like we said at the beginning, if it's rational, it's going to terminate. If it's irrational, you're going to have some sort of periodicity in there. Cool. Please let me know if that was too fast. I just think because it's quite algorithmic, once you understand that step, you just apply that. You just keep working through it. So yeah, so please let me know if you want me to touch on that again or explain any part out deeper. Let's go back the other way. Let's start with a continued fraction, and let's come back to where we started. So we've got 0, semicolon, 2, and then 2 and 1 are repeating here. So we can begin. So like the tip gave us before, let's start with this part, because this is going to be the trickiest part, and then let's handle the other parts as they come. Okay, so just focusing on this part, what does this represent? So let's call this x. Let's call this section of it x. Give it a label, and let's start to write it out. So if it repeats, so the way we write these continued fractions is we write this number in the denominator plus 1 on the next number, and then we keep going. Because this is repeating, well, we can substitute this part as x, because that's what it is. It's going to go on forever, and that's just x. Okay, great. So now we've got an expression here that's actually determinate. We can actually find out what this is saying. So x is equal to this expression here. Okay, let's solve for x. So then we're going to expand this fraction on the bottom here. We're going to flip it. These are all just like bits of algebra that I'm sure you guys are able to handle. So you move through this. Okay, great. We get this expression. This is just going to give us a quadratic. We know how to solve quadratics. So we move things over. Okay, great. We end up with this quadratic. We use the quadratic formula. We get to this. Beautiful. We want to take the positive one because that's just the nature of what we're working with in now. We want to take the positive solution. So that's what we're considering. So we take that positive solution from the quadratic formula, and that gives us this. Right? We notice it was repeating. It gives us something irrational. Makes sense. It's all working out. Great. So we found x. We found x by just using the simple trick of just saying, well, if something's repeating, let's give it a name, so we can actually like get our hands on it and start to figure it out. Great. So we've got that, and let's start to look at the other parts. Okay. So we've got a 0. That's our integer part. Cool. 0 plus 1 on. So our first part of the denominator is 2 plus. Well, we already know what this is. We found this as x. We know exactly what that is. So if we substitute that in, we can expand, and we can try and solve, and then we get this beautiful expression here: 3 minus root 3 all on 3. Which, I don't know, it just looks really nice. I think it's cool. Cool, and that's our final answer. So the tricky thing here was we're just dealing with that periodicity. So we figured that out first, and then we just use that answer and then substitute into the rest. Cool. Beautiful. Okay, so we're up to chapter 3. Okay, we're a bit later than I wanted to, but that's alright. So let's take a second, have a breather, and then we'll get into the last two topics before we continue forward. So just take a second, maybe stretch your legs if you want, have a drink, and then we'll get into the next bit. Cool. If there's any questions, throw them in and I'll keep an eye on the chat. Continuous fractions is very cool. I agree. It's like it's just crazy that it's so simple and it works. It's just a cool way to represent numbers. This is a whole bunch of fractions. If anyone else has any parts that they think are really cool, let me know. If anyone has any favourite parts of math they want to throw in the chat, go for it. We might get started back up, just so we finish as close to on time as we can. Cool. This is one of my favourite topics, modular arithmetic. Like I said, this whole course is one of my favourite courses. And then like you use this again, like I've said 400 times now in 3521, which probably is my favourite math course. It can also represent the irrationality, yeah, which is really cool. Like you just get the number of digits between two brackets, and it represents this whole complexity of a number. It's really cool. It's just so simple and so determinate as well. Because there's something that's a bit tricky with irrational numbers is the fact that you can't just write them down. Like it would take you an infinite amount of time to write down the digits. Cool. Let's get stuck into it. So, modular arithmetic. Here we go. So we're going to start off by talking about the congruence relation. So, for a and n and z, two integers, we say a mod n is the remainder in n obtained when a is divided by n. So that is r if a is equal to n times a quotient plus r. Because we say that these two integers are congruent modulo n, or a is congruent to b modulo n. We write it in this way, and there's a whole bunch of stuff with this, but I'm sure you guys know this. Always a quick comment. It's such a hard problem, but if we know it's a key fraction formula, we know how. We know straight away whether it's rational. Yeah, 100%. Yeah, Gerald hit the nail on the head. Cool. All right, so we've got a couple of properties here that we can look at. So we've got two numbers. So if a is congruent to b and c is congruent to d, both modulo n, then when we add a and c, it's essentially adding b and d, right? So like, where's it? Here we go. So let's work mod 3, just because it's nice and small, so it'll be easy for this example, right? So if we're talking about 4, right, we know that's congruent to 1. So we've got 5, that's congruent to modulo 2. And what this is essentially saying is 4 and 5, well, that's the same as 1 and 2, right? Because these guys will give us 9, and these guys will give us 3, and they're both congruent to 0. That's what we're saying here. And then you've got a similar thing with multiplication. and then like this one is essentially just number 2, just done a bunch of times. Cool. Interestingly, the congruence relation is an equivalence relation on the integers. If that means anything to you, then that's good. This doesn't really come up much in terms of problems, but in terms of like understanding, wrapping your head around like this idea, especially like this part, is helpful, I think. Yeah, so just like having a think through that, I think that helps you just like get your head around what is actually happening in a more abstract way. Great. So we've talked about commutative rings. So the using the natural definition of addition and multiplication, we've got Zn, so the integers modulo sum n, is a commutative ring with identity, right? And these are these extra things that we're adding on to the rest of the definition. Cool. All right, let's do a question. So by working modulo 3, there you go, modulo 3 again, show that 2 to the power of 2 to the power of n, so it should be clear, this is 2 to the power of 2 to the power of n. So 2 to the power of n is its own number here. Plus 5 is always a composite for every positive integer n. Now you might look at this and go like, how the heck am I supposed to do this? Don't understand, but it's not too bad. There's a little trick we're going to use. So modulo 3, so there's got to be some trick in there. So we start modulo 3. Oh, this should be a 3. So working modulo 3, okay, so we know that a plus 5, right, is, well, like a plus 5 is congruent to 2, which is congruent to -1 as well. Okay, so that might be a bit confusing. I'm sure you would have seen that at some point in the course, but yeah, remember these things wrap around the whole way around. So we can say that plus 5 is the same as -1. Okay, well now we've got, it might not look like it, but essentially what we've got is a difference of 2 squares. It might take a second to wrap your head around, but what we've essentially got is a difference of 2 squares. Right, and what we can do is we can split that up then. And then once we split that up, hold on a second. Sorry, this slide is a mess. Just adding those in there. We can split this up into a difference of 2 squares, and we'll actually, regardless of what this power is up here, you can see that we've got a power of 2, and we're looking at the numbers either side of it, so plus minus 1. So if you're thinking about 3 consecutive integers, well, one of them is guaranteed to be divisible by 3, right? And we can motivate this by saying, like, if we look at 2, 3, 4, right? You can think of like 2, 3, 4. So the middle one's divisible by 3, or you can think about like 6, 7, 8. The first one's divisible by 3, right? Yeah, so you got a number separated by you're looking at the numbers either side of a power of 2, and one of them is divisible by 3. So therefore, this thing's going to be congruent to 0, actually. So then, if it's congruent to 0, we can say that it's equal to some integer times 3, right? It's equal to 3 something. Cool. So now that we know that we've shown it's equal to 3 times something, right? The only way that then this can be a prime number is if k is equal to 1. So if we try and see if this is possible, we look at this expression, we go, okay, well, we know that we're looking at positive integers n, right? And then we use this condition and we work through and we see, well, this is a contradiction. You know, we said that k had to be 1. Well, we're saying that now k has to be greater than or equal to 3. Surely that can't be true. So we've reached a contradiction. So therefore, we say that it's always composite for every positive integer n. Cool. Can we use FLT? Matthew, Brian, would you be able to write out what FLT stands for? And then I'll probably be better positioned to answer that question. Cool. If need be, I can come back to it and we can figure that out together. Cool, let's talk about inverses. So inverses in Zn. So it says here a non-zero A in Zn has an inverse if and only if the GCD of those two numbers is 1. Cool. Okay, so we talked about this before. We said the GCD of two numbers means that they're relatively prime, right? And when we're talking about this, when we're talking about this, we want to make sure that all the numbers that are relatively prime to this are going to have their own inverse. Oh, for miles. Okay, cool. Let me keep working through this, and we'll touch on that in a sec. Cool. Yeah, a non-zero A in Zn has an inverse if and only if the GCD is 1. Yeah, because GCD 1 means that they're relatively prime, and we want to find all the ones that are relatively prime because those are the ones that have inverses. Cool. Yeah, this is something we touched on before, just reiterating, building it up because we're going to use them in an example. Cool. And then groups. So the definition of a group. So we've looked at rings, and we talked about then commutative rings with identity and adding inverses in them to create a field. Multiplicative inverses to create a field. Now, if we look at the definition of a group, okay, so we say let G be a non-empty set whose elements satisfy the following 5 rules. So we've got closure. So we're going to have some sort of group operation connected to this set, right? So we have G, and let's just say we have multiplication, right? If we have those two together, so it's closed under the group operation. It's associative under the group operation. Skipping this one for a second, we've got existence of an identity. We've got the existence of element inverses. So we've got an inverse for every element. Then what we can also say, we can say that if this group is commutative under the group operation, we can call this an abelian group. So it's a commutative group. Cool. And then there's a little comment underneath there. Yes. Okay. Cool. There's a little comment that the set Zn forms a commutative group under the operation of addition. The identity is 0, but not under multiplication. So under multiplication, it doesn't form an abelian group, but under the operation of addition, it does. Cool. Okay, so this is going to get into a cool little question in a second. So common tests for divisibility. So let's just run through some of the more standard ones. These are useful all the time in maths. Like, I shouldn't say all the time. It's not useful for everything you do, but they're really useful as just quick little checks to make sure you're on the right path with things. You know, just make sure what you're saying is true and that you're on the right path to what you're doing. So we say a number is divisible by 2 if and only if the last digit is divisible by 2, right? So if it's an even number, there's a 2 in there for sure. A number is divisible by 4 if and only if the last 2 digits form a number which is divisible by 4, right? So like, let's just say the last 2 digits are 1 and 6, so 16. So that would mean that no matter what's in front of it, the rest of the number is divisible by 4. Cool. And like that's because you want to make sure you can take 2 powers of 2 out of it, out of the number essentially. A number is divisible by 5 to the a if and only if the last a digits are divisible by 5 to the a. Now this was interesting. I had to remind myself of this because I was only familiar with like this kind of idea. This is really cool. So 5 to the a if the last a digits are divisible by 5 to the a. A number is divisible by 9 or 3 if and only if the sum of the digits is divisible by 9 or 3 respectively. This is one that I use all the time. So you just quickly add up the digits and you just test for that divisibility. And then the test for 7 is a bit tricky. So you double the last digit, you subtract it from the remaining truncated number. If the result is divisible by 7, then so is the original number. So this one's got a bit of an algorithm to it. I'm sure there's probably some other way to do it, but I don't know if it's any less algorithmic. This is the one that's recommended in the lecture notes. Cool. Let's do a question. So test the number. I'm not even going to try and turn it into millions and all that kind of stuff. So 7689627, turning that number, testing that number for divisibility by 9, 11, 13, and 17. Cool. So let's start off. First, we'll test by divisibility by 9, because it's the easiest. Well, I think it's the easiest. So we'll start with 9. So what we do is we just add up all the digits and we check if it's divisible by 9. Right? And we add up all the digits and we can do that, and then we see it's divisible by 9, so therefore we can assume that the original number is divisible by 9 as well. Cool, so this one's not too bad, it's a bit of a warm-up. Okay, let's look at 11. Great, so we've got this alternate sum test for 11, and the way we can, like, if you haven't seen this before, you probably have come across it somewhere, but you haven't seen it before. The way this works is because each of the powers of 10, because we're working in base 10, each of the powers of 10 are alternatively congruent to 1 or minus 1 modulo 11, right? So you've got 10 is congruent to minus 1 mod 11, and then you've got 100 is congruent to 1 mod 11, right? Because 99 plus 1 is 100. And then an even easier way you can think about it is 100 is then 10 times 10, so it's 10 times this, so it's minus 10, which is then 1, which is what we wrote before, and then you can just keep multiplying by 10, and it's going to keep alternating. Right, so then when you split each digit into like 7 times its power of 10, 6 times its power of 10, all those powers of 10 are just going to turn into plus or minus 1s. And so then you can just add in, you just alternate each one. And it actually doesn't matter if you start with the negative or the plus, as long as you are consistent and you're alternating. So usually people just want to write down the number, right? And then technically that's a plus in front. So usually then you would start with a minus for the next one. Because you can't necessarily do this, because then you've got plus, and then you've broken up the pattern a little bit. Yeah, so that's that alternate sum test for 11. And yeah, it doesn't. Sorry, yeah, that's what I was trying to say before. As long as you're consistent, it doesn't matter if you start with a negative or a plus, because you get that's just like multiplying the whole thing by -1, and you're going to still get the same divisibility property regardless. Cool. So in this instance, we find that 11 is divisible by 11, which is good. It's a bit of a sanity check there. And then we concluded the original number is divisible by 11 as well. So we move forward. Testing divisibility by 13 and 17 will require some deeper thinking. Cool. So the test for 13 that is developed in this answer is it's going to require a bit of guess and check for a second, but then we can figure out that 11 is congruent to -1 mod n. Right? We can use this. So it says here, so we can apply a similar alternating sum test to 11, except now we need to group 3 digits at a time, starting from the right. Cool. So instead of breaking up each digit and its power of 10, like we've got a group of 3 digits and a power of 1,000, and those thousands are going to turn into ones or -1s or +1s, and so we're going to alternate that way. And again, we just got to make sure we're consistent with it. So then we use the alternate sum test. So it's very similar to the one for 11. It's just we've got a different property because 13 has different properties to 11. Cool. So we use this test, and then we find that actually in this instance, 13 doesn't divide the number, unfortunately. Cool. So, oh wait, hold on a second. There's a bit of an inconsistency here. Let me just fix this up and make sure that what I'm saying is correct. Yeah, cool. Sorry about that, just making sure the slides are consistent. And this should be here as well. Cool. Okay, for 17, this is a bit more convoluted. So let's begin by trying to develop a method similar to the test for divisibility by 7. Okay, so if we look at the test for divisibility by 7, and the reason this came to my mind is because the 17, there's a 7 in there, so I was like trying to think of a test, and I tried to like think of one that would work like 11 and 13 with the alternate sum. Couldn't think of anything like quite quickly, so then I was like, okay, but what about if we try and do something like we did for 7, where you take a number off the end, but yeah, you do an operation and you go, is that number divisible? And then you go, okay, well, I need to do another operation, and you keep working through it until you find something that you can say definitively this is or is not divisible by the number you're looking at. So the way 7 works is you take away, I think it's 2 times the last digit from the rest of the number. So if we make this a bit abstract, we say, well, let's take a multiple y of the last digit from the rest of the number. So we've got this whole number here, right? And we're saying take y of these last digits. So take y of these away from the rest of the number, and then let's see what happens from there. So n is this original number here. Take away this last digit, so then it'll be 7689620, and then divide it by 10, so we can get rid of that 0. So then we're working with the rest of the number. So this is the rest of the number, and we're taking y multiples of b. And now let's just say we do that, and then we've chosen y in such a way that what we get is divisible by 17. Let's just say it's 17 times some number x, right? And all of these numbers are just positive integers. So, okay, just to reiterate, we're saying, okay, let's take some multiple of b, which is the last digit. Let's take some multiple of the last digit away from the rest of the number. Let's do that, and then let's say it is divisible by 17. What happens then? What value of y would I take away that would help me guarantee that this is true? So we work through this. Oops. So we work through this. So we got the original number. We've got this digit we're taking away, and we're saying that it's divisible by 17. It's 17 times something. So then what we do is we do a whole bunch of rearranging. We move some stuff around. We want to represent this original number and see if we can find something that would mean the original number is divisible by 17. So I've done all this rearranging, move stuff around, and then we get this expression. So then we go, okay, so n is equal to 17 times something. So the original number is divisible by 17 on one condition. If we can guarantee that this is some sort of integer, then we'll have done it, because the original number is an integer. So if we take a step back for a second, what are we saying? Okay, we're saying we're going to take the last digit, we're going to take a multiple of y from it, work through it, and represent the original number as a multiple of 17 times something. And because the original number is an integer, we need to make sure it's 17 times an integer, because that'll give us what we want. Okay, well then that's fine, that's an integer, that's an integer. This looks like a fraction. Okay, so there's a bit of an issue there. So we need to choose this numerator such that it's divisible by 17, right? Because if we can choose that, then this will be an integer as well. The whole thing will work out nicely. So how do we choose that? Okay, let's have a look. So we work through a couple of options. We go y equals 1, and that doesn't work. That gives 11 over 17. It's one positive integer. Y equals 2, it doesn't give us a positive integer. We keep going. We find that once we get to y equals 5, right, this becomes 50. We get 51. 51 over 17 is 3. Yep, it's 3. That's an integer. right? So we don't need to keep working. We don't need to go to the next part. We don't need to try a whole bunch of other integers. This one works. Let's use it. So y equals 5. So it says, this is saying that if we get the last digit and we subtract 5 multiples of that last digit from that number, and if we get something that's divisible by 17, well then the original number is 17. It is divisible by 17. Not is 17. That would be bad. If you did that, if you subtracted 5 and then just got 17 as the original number, that's a bit weird. But what we're saying is that subtracting 5 times the last digit from this number, if that's divisible by 17, the original number is also divisible by 17. Okay, we can test this out. So we work our way down this cool little triangle adjacent shape, well, trapezium, technically. We work our way through that and we get to something, we go, okay, we got 51. Lucky us, because we already know that's divisible by 17. Right, so we worked through it and we found, okay, so 17 divides the thing at the end of this sequence, and we've guaranteed that this sequence means that if we find something divisible by 17 at the bottom, we can apply that on the way up, and then we get the original number is also divisible by 17. Yeah. Cool. All right. Linear congruence equations. Let me just check anything. I haven't forgotten about the question that we asked before. I just want to make sure that I am able to hit all the points that we need to hit for these other things, and then hopefully at the end I can quickly have a think about it. We can figure out that question. Great. Okay. Linear congruence equations. So the simplest congruence problems are linear congruences. These are easy to solve over Q, but much more interesting to solve over Zn. This is because over Zn, so we're saying it's not necessarily a prime, so we're saying n is an integer. We don't know if you have an inverse or not, so sometimes these are quite interesting to solve. Cool, okay, so let me just double check. Yeah, cool, so we're building up to this. Great. Okay, so suppose that n is a positive integer and d is the GCD of a and n, right? So these are some rules that are important to remember. The equation ax congruent to b mod n has a solution if and only if d divides b. So we're saying that there's a common factor, there's a GCD of these two numbers other than 1. If that's true, then this has to also be divisible by d. Otherwise, we don't have a solution. So that's important to remember. Actually, I think, what did I write? Yeah, this theorem is really important to remember, as you'd hate to waste time in an exam trying to solve linear congruence only to get to the end and realize it doesn't have a solution. So it's important to remember these things, because then you look at it straight away and you go, no solution, you just write no solution and move on to the next thing. Yeah. And knowing Igor, he tends to put those in a lot of places. He tends to put something in, and then you spend a lot of time working on it, and you're like, oh, it actually has no solution. If you're like me and you're silly and you forget to do this check. Moreover, if d divides b and a divides d a prime and divides d n prime and b divides d b prime. Okay, so we're saying, so if we need to check that d divides b, right? Because if it does, we have a solution. Otherwise, we don't. So we're saying that if d does divide b, right, then we can cancel out this factor, and then we have this new congruence over here that we can work with. Yeah. Then we've got to remember that when we're talking the original modulus, then you've got then you've got d solutions when you return to the original modulus as well. So you've got to remember that if the question says express your solution in terms of the original modulus. What is a Diophantine equation? So Diophantine equation is an equation where we seek only integer solutions. So these are like a special case, quite an interesting case, I think. So this is talking about different cases of them. Yeah, so important to note that the equation ax plus by c, where a, b, and c are integers, has a solution if and only if d divides c, where d is the GCD of a, b. So why do we know this to be true? So have a think about that. there's some stuff we talked about before that means that that's why that's true. Have a think about that. Cool. Let's do a question. Great. So 2016 paper. So find all integers x and y with 4x plus 5y equal 18. So this is an extension of linear combinations for GCD. So this is an extension of linear combinations for GCD. Oh, are you talking about this thing? So this is an extension of linear combination for GCD. What do you think? Yeah, okay, yeah, kind of. Yeah, I think I get what you're saying. Yeah, it's like an abstract way of saying that, I guess. Like, because I think, if I'm right, what you're trying to say is, like, because you've got these x and y, you're saying it can be, like, any multiple of these. Like, you can have, right, so if you've got the GCD on one side of the equation, then you've got x and y, which can be any number. You've got all these different options of them. Yeah, I get what you're saying. Yeah, well, actually, it's funny you say that. So we're going to do this, and I guess this kind of answers your question in a sense as well. So find all integers x and y with 4x plus 5y equal to 18. How many of these solutions lie in the positive quadrant? So we'll get to that in a second. First of all, let's find all the solutions. Let's find all solutions x and y. I realize it sounds like a funny sentence. Let's just find all the solutions. Let's just do it. The DC part. This is it. Oh, exactly. Cool. So let's get started with it. So to do this, to simplify, so we've got x and a y, right? And we've got no other equation to help us out, right? What's the phrase you say? Like, you want to have the same number of equations as the number of unknowns you have. This instance, we've got two unknowns. We've got one equation. So we're going to have to go around it in a different kind of way. And we want to find only integer solutions. That's why it's a linear Diophantine equation. Named after Diophantus, I think. Ancient Greek. I think that's right. So we need to consider a modulus. It's going to isolate one of these variables. And I like to look at the one with the smallest coefficient first. So I'm going to try and get rid of the 5y first. That's just how I prefer to do it. It doesn't really matter, but I just like to do it that way. Because then you tend to work with smaller numbers, in my experience. Cool. Okay, it's great. So we're going to consider everything mod 5. So that means that this guy's going to be congruent to 0. And then we say this guy's congruent to 3. Okay, so now we need to multiply both sides. Well, okay, so we need to multiply both sides by the inverse of 4 because we want to get rid of 4. What you would usually do is you would like divide both sides by 4. So you'd go like 4x. Well, it's congruent here, but let's just say it was equal to. You'd go like, oh, divide by 4, that's fine. But that's only because a quarter is the inverse of 4 in the field that we're used to working in. But we don't have that same luxury here. So we have to multiply by the inverse of 4. And we're working mod 5, so there is an inverse, which is good. Right? So then I the way I think about it is I go, okay, well, what can I multiply by 4? It gets me a number that's going to be congruent to 1. So then I go 4 times 4 is 16, congruent to 1 mod 5. Great, so we multiply both sides by 4. That gives us this, then we can simplify, so that's going to be 1, and that's going to simplify to 2. So we've got this, and another way of writing that is x is equal to 2 plus some multiple of 5, where this can be any integer, plus or minus. Right, so we've found a solution for x. We've introduced another variable, so you might think we're going in the wrong direction. Actually, I think I call it t on the next page, so let's call it t here. But actually, this is on the way to solving it. So x is 2 plus 5 times t. Great, so let's substitute back in the original equation, and let's try and get y in terms of t. So then we can do some cool stuff from there. So we sub it back in. We won't necessarily go through all this because you just work through it and you get to this. So you get y in terms of t as well. So now we've got x and y in terms of t. Well, technically that's our solution for all x and y. We can say that you can pick any t in the positive or negative integers, and then this will give you a solution x and y that solves this equation, right? And let's just quickly test this out. I don't know. Let's see if it works. T is 1, so then x is 7, y is -2, so we've got 28 minus 10, 18. Cool. It's good it works. If it didn't, it would have been really embarrassing. But yeah, it works. Great. Well, then it says how many of these solutions lie in the positive quadrant. So we're going to figure out not only how many, but we're just going to find which ones they are. Okay, great. So if it's in the positive quadrant, if we think about it, right? So this is x, and this is y, right? So x and y are both positive here. So, let's write it like this: both positive. X is negative, y is positive. What's this? X is negative, y is negative, and then here we've got x is positive, y is negative. So this is first quadrant over here, where x and y are both positive. So if we restrict x and y to both be positive, we say they must be greater than 0. So what we're going to do is we're going to find these two conditions for t, and then we're just going to say, well, okay, ensuring that both of these conditions are true, which values of t can we use? And then that'll give us our solutions for x and y. So we solve this, we say, okay, with t is going to be, and remember here, t is an integer. That doesn't look like anything, that looks like scribble, but it says that t is an integer. So we've got to remember this. So t is greater than -2 on 5. Yeah, it's not greater than or equal to because we're looking strictly positive here. So if it's an integer greater than -2 on 5, well, it's going to be greater than or equal to 0. So t is greater than or equal to 0. Okay, we can work with that. Let's try the other one. So we go on the other side, and then we see, well, if we look at the equation for y, this tells us that t is less than a half, less than 0.5. So then that means if it's an integer, it's less than or equal to 0. Well, okay, so we've got this condition that 0 is less than or equal to t is less than 0, right? And there's only one integer that's going to satisfy that equation, which is then t then must be equal to 0. That's the only one that we can find. So then if t is equal to 0, we substitute that in, and then that gives us this solution here, right? Yeah, so if we sub it in there, that gets 0, that's 0, so we get the solution 2, 2. And you can also, you can kind of, if you look at this, sorry, I'm flipping back and forth a lot. If you look at this, you can kind of look at it and see that this is true, right? Even without doing that secondary solution, you kind of look at it and go well, if I change t in the positive direction, then x is going to grow, but y is going to immediately go negative. And yeah, so they're going to go in opposite directions. And then if you make t negative, they're going to do the opposite. So they're immediately heading in opposite directions. So the only solution that works is if you just start in the middle at 0. Cool. Great. Just considering time and the fact that I'm going to quickly run through the Chinese remainder theorem. Just the idea of it really quick, and then what we're going to do is we're going to move forward to the last topic just to make sure we are able to cover everything. So the Chinese remainder theorem is a way when you're dealing with many of these. Let me just check. Yeah. Okay, cool. The Chinese remainder theorem is a way when you're dealing with lots of these different congruence equations. It's a way of helping you solve them in a systematic way. So you've got the simultaneous equations or congruences saying all these things. So you've got a whole bunch of them. So this is the algorithm. So you let n be the product of all the different moduli, whatever you want to call it. And then your solution at the end that you're going to find is going to be modulo that final that modulus that you just found there. That's what your final answer is going to be. Something really important to remember is to make sure that you're dealing with where does it say here? Yeah, this is the most important bit when you do Chinese remainder theorem questions. The GCD of all of these moduli has to be 1. It's really important to consider. Yeah. I'm just trying to think if there's anything else to touch on. So yeah, so you do this for each I. You define m is going to be this with the modulus corresponding to that one factored out, right? So then you define yi solving the congruence, mi yi. So yeah, so this will be then n on ni. So you factor out that one, and you're going to solve this congruence. And you can do that in whatever way makes the most sense. If it's an easy one, you can just do it straight off your head. So then what you need to do is then you're going to find all of these results. You're going to find all of these results, and then what you want to do is you're going to create them together modulo this modulus, which is the product of all the individual ones. Yeah, cool. I think that's all the really important things to cover. This is a big consideration when you're doing Chinese remainder theorem questions. Make sure you remember that they all have to be coprime. Yeah. Cool. All right. Powers and roots. Okay, great. Let's talk about this. So for Mars' little theorem. So suppose that P is prime, then any integer A satisfies the property that a to the power P is congruent to A mod P. Additionally, if A is not divisible by P, then A satisfies the property A to the power P minus 1 is congruent to P, is congruent to 1 mod P. Great. I can't remember which instance. Oh no, I do remember actually. This instance comes first because this is a special case. I think this is said later on. This is a special case of a more general result. And then I guess, especially if A is not divisible, if A, any integer, yeah, and then I guess then you can infer this off of that. I think that's the way it came about. Either way, these are both very useful tools. Great. Then talking about Euler's phi function. So we're going to build up to that general result that I talked about as well. Yeah. So what was the topic we were talking about before? My mind's going blank now. When we were talking about when we were talking about linear congruences, and we were saying if you've got the AX, and if you've got the A there and you've got the N, and there's a GCD there other than 1, you've got to make sure that the B that you're looking at is also divisible by D. So it's like a similar condition to that. Yes, you've got to check that, otherwise you don't have a solution. Well, yeah, it just means that we cannot use CRT. Yeah, exactly. Yeah, I might keep moving on with this content, and it looks like Gerald's on top of it, but I'll come back and check in and make sure that it's all sorted for you, Matthew. Cool. So for the phi function, we define phi of n to count the number of relatively prime integers smaller than n. So some properties of it. So we have this multiplicative identity. If the GCD of m and n, so these two numbers, if they're relatively prime, so the GCD is 1, we can kind of split up this function. So we split it up into these two things. And if you think about that, if you think about the fact they're relatively prime and they don't share any prime factors, you can kind of figure out how this comes about. Cool. And then so we let P1 up to Pk be the unique prime factors of n. Then we have this formula, which is always super useful to find phi of n. And it looks like quite daunting. It looks quite difficult, but it's actually not too bad to compute. It's actually not too bad when you're dealing with nicer numbers. It's actually not too bad, and it can sometimes be more time saving than doing it in other ways. Cool. And then we have this last property. excuse me, which is what I was alluding to before when I was saying that the Fermat's little theorem, we had like a special case of a more general result, and this is how we get that special case, because it says if n is prime, then the phi function is just n minus 1. Great. Okay, cool. Let's check how we're going. Let p be an odd prime. So find another integer n such that 5n is equal to 5p. Okay, so the trick here is we want to be able to find something that is out the front here that's actually just 1. So we're going to use this identity we talked about before. Where does it introduce it? Yeah, cool, okay. So since p is an odd prime, and every integer smaller than p is relatively prime to b. That makes sense, right? So if p is an odd prime, which means that it's just a prime that's not 2, right? Every integer smaller than p is prime to p. Cool. In other words, the GCD of m and p is 1 for every number between 1 and p. So that means because they're relatively prime and the GCD is 1, if we took some arbitrary number m and p and we took the product of those, when we try and find the phi function of that, we can separate it, right? And it doesn't matter which m we choose, as long as it's less than p, it'll work because the GCD is 1. So we split it up. Then we're going to use the fact that 2 is prime. So yeah, so since 2 is prime, then the way we find the phi function is we get 5, 2 is 2 minus 1 equal to 1. So like I said, we're gonna be sneaky, and we're gonna try and just find that that's 1. Because if that's 1, then we have this identity here. Alright, and then we just call this n and we call it a day. So in other words, we have 5 2p is equal to 5 2 times 5p, which we've said this is 1, so it's just 5p. So it suffices to choose n as 2p, because it just says find another integer n. It doesn't say find all of them, it just says find one. So we say, okay, this one works, let's call n 2p, and let's just say that works. Cool, so the trick here was trying to find, so this one has to be prime, well this one has to be an odd prime, and this is kind of helping you a little bit, because we can put 2 in here and it's not going to do anything, because if p was any prime, it could be 2, and so then n would be 2 squared equal to 4, and then that messes things up for us a little bit. Cool. Alright, so show that there are infinitely many positive integers n such that 10 divides the phi function of n. Cool, I think we're going to do this one. Yeah, great. And then we'll keep pushing forward. Okay, great. So, show there are infinitely many positive integers n such that 10 divides the phi function of n. So, okay, there's a couple of approaches we can take to this. I think there's 2 methods listed here. We're just going to talk through the first one. So, the way we're going to think about this, right, is so 10 has to divide the phi function of n. So, we've got to think about, does the formula pop up straight away? Yeah, this is the formula I'm wanting. So notice here, we've got a factor of n at the front. Okay. So if we can make it that we choose n such that 10 divides n, if we can get the rest of it to work out, then we'll get the result that's true. We'll get a result that's true. Right? And we want to choose infinitely many. So let's create a number that's divisible by 10 in the most arbitrary sense, in the broadest sense we can say. So we claim that n is going to be 5 to the power alpha times 2 to the power of beta. Okay, so this is an arbitrary way of saying that we've got something divisible by 10, because the prime factors of 10 are 2 and 5, and we're just going to take some product of these two factors, right? A, b greater than or equal to 2. We claim that AB greater than 2 satisfies the condition. We haven't shown this yet, but we're going to claim that satisfies the condition. Yeah, 100%. So yeah. So you'll see in the slides there's a secondary solution that follows that kind of logic. Yeah, yeah, exactly. So you seem like you're pretty well across this kind of stuff. So this first solution we're going to look at. So we've picked a number that is guaranteed to be divisible by 10, and we've made it arbitrary so we can try and hopefully find infinitely many of them. So we use this formula, and this one doesn't care about the powers. We just substitute what the factor is. We work through, and then we get something equivalent to this. Okay, great. Well, the only thing left to do is just guarantee that we get a positive integer. That's all we got to guarantee. We got to guarantee we get a positive integer, and then we've got to get a positive integer here because this is the answer to the phi function. Okay, so we say that as long as alpha and beta are greater than or equal to 2, well then we should be okay. Because if alpha is equal to let me say 0, oh, that was a messy 0, right? Then 5 is negative 2, so that's 1 on 25. We're not in a good place. But as long as we say alpha and beta are 2, or if they're greater than 2, then we get something that works. Cool, so therefore, because there's infinitely many numbers greater than 2, we found infinitely many positive solutions, such that 10 divides 5n. Yeah, and the trick was finding something here that's always divisible by n, but has enough room that you can find infinitely many of them. And then, yeah, exactly. Yeah, and then that's, so Matthew's kind of written what's on this next page here. Yeah, cool. All right. So, Euler's theorem. We begin to generalize Fermat's little theorem. So we say Euler's theorem, let a and n be integers such that the GCD of a and n is 1. Then a to the phi function of n is congruent to 1 mod n. So this is the general idea of Fermat's little theorem. So yeah, just generalized, yeah, exactly. Generalized FLT, as our friend Matthew would say. Cool. Yeah, great. We can use this to greatly reduce the number of computations used to find powers. Great. Sorry, I'm just checking through here because I want to make sure we don't go too much over time. Yeah, cool. Okay. Cool. So I'm just going to give you the quick outline of this. Sorry, guys. Let me just get rid of this. I'm going to give you the quick outline of this over here, and then I'm going to keep pushing forward. So what you want to do is you want to find the phi function of this. We're going to use that formula we had. So we want to find that 37 to the phi function of 52 is congruent to 1 mod 52. Right, so it's about finding what this is, and once you find what that is, you're going to see that then this is a result that comes out of that. Cool. Great. Primitive roots. Okay, this is something that's important. Cool. Primitive roots. So the order of an element a in Zn is the smallest positive integer k, such that a to the power k is congruent to 1 mod n. So the word order gets thrown around a lot, and you can use it for a lot of different things. You can talk about the order of the set. You can talk about the order of other things, but talk about the order of an element, and the order of the element is the smallest positive integer k, such that a to the k is congruent to 1 in that set. Now units. So units of a ring are the elements that have multiplicative inverse. So they're the elements that have GCD equal to 1, right? The set of units. Yes, these ones that are all relatively prime to the n that you're talking about in this instance. So the set of units, we call it Z star. It forms a group under multiplication, right? And we can see that this is definitely true. Because so the number of units. So a unit is one that's relatively prime, and the phi function counts the numbers that are relatively prime to n. So therefore, the size of this group that we formed is the same as the phi function. Cool. And our primitive element, so we're building up this definition that a primitive element of Zn is an element whose order is phi of n, right? So you're going to find that the order of all these elements. So let's just say phi of n is 4, right? You're going to find the orders of these elements are going to be something like 1, 2, or 4. Right, and we're saying that the primitive ones are the ones that have order 4 in this example. Right, and this is going to be useful when we get to a question. This is exactly how we run through the question. So there's a question here, and it's really helpful because it's all laid out. It's laid out in a table. It's giving you all the information you need, right? So what we're saying, which of the numbers 2, 3, and 7 are primitive elements in Z star, and give brief reasons. Okay, so like I was saying, so you want the order of the elements, so the power that's going to give you that the number is congruent to 1, you want it to be the size of the group of units, or we can say we want it to be equal to the Euler function of n, right? So yeah, so I guess we're assuming this is prime because then we find n minus 1 and we get this, and this is the factorization of it. So yeah, which of these are primitive elements? So from here we can quite clearly see that 3 is congruent to 1, to this power, way too early. So it's already congruent to 1. It's congruent to 1 when we haven't had to raise it to the value of the phi function. So we say that 3 is not a primitive element, right? So then we can say that then 2 and 7 are primitive elements. So let me just check if there's any extra information here. Yeah, we can see that 3 cannot be a primitive element because we've already got congruent to 1. Yeah. And then so therefore we say that 2 and 7 are. Yeah, cool. Cool. And then so it says here, we begin to classify the existence of primitive roots in an arbitrary modulo n ring. So these are just some rules that you can use to work at a higher order level, so you don't have to go into the nuts and bolts and check things. You can just look at these conditions and say, because the hard work is hidden under the surface, because there's all these rules and conditions and stuff that have been checked and worked with to prove that these are true. So then we can operate at a higher level and say, okay, well, if we just find these conditions are true, one of these conditions are true, then we know that primitive roots exist, and we're just proving existence here. We're just seeing if there are primitive roots. Cool. So these are our 3 conditions here. So we're going to use this example here. So what is the largest integer n less than or equal to 57 such that Z star has a primitive root? Cool. Okay, so let's work through each of these groups. I think they come up on this slide. Yeah, great. Let's it says here, we look at the possible values of n in one of the forms. So we can't guarantee at this point, but looking at 57 and how far away it is from 1, 2, or 4, I'm assuming we can find one between 4 and 57. So let's just say tentatively it's not in that group. Then we can start to look at these 2 groups, and then if we really don't find anything by the time we get to 4, then we can have a look at those ones. But let's get started here. So there we go. So the biggest prime, so if we look at here, if we look at odd primes, the biggest odd prime, smaller than 57, is 53. So okay, so 53 works. Right, we've got an odd prime. So using this criteria, it'd be 53 to the power of 1. Okay, so we've got something. So then we can definitely rule this out because we've got something bigger than 4. Okay, great. So then we check, okay, can we find one that's bigger than 53? Can we find one between 53 and 57 that maybe falls into this instance? Because this is the largest one of this instance we can find. But using this last category, can we find something that's 2 times a power of a prime? Power of an odd prime, I should say. So we check 54, 55, 56, 57. So 54, we have a look, and we go, okay, so 54 is 2 times 27. 27 is 3 cubed. Okay, 54 works, that's good. Great, so we've got another one. So now we can actually kind of cross this off, and we can say, well, actually, 54 is the biggest one we can find at the moment, because it's 2 times 3 cubed. So that's our new biggest. Okay, let's see if we can get any bigger. So 55. 55 is 5 and 11. It doesn't fall into any of our criteria. 56 is 2 times 28, but 28 is not a power of a prime. of no prime. So 56 doesn't work, so where's 55? 55 no, 56 no. Actually, I'll do them like this. 5 no, 56 no. So the last one to check really is 57. So we look at 57, we see 57 is 3 times 19, so it's 2 primes multiplied together, but it doesn't really fall into our criteria. So, and 57 doesn't work either. So then the largest integer n less than or equal to 57 such that z star has a primitive root is 54. So that means that you can guarantee that z star 54 will have a primitive root based on this criteria that we've set up. And like, I know sometimes it's hard with these kinds of things when you just have to follow a thing and assume that it's true. If you go further with this stuff, you get to learn like why these are the cases, why these are true. But for now, you can just you can assume that the work has been done to prove that these cases are the right ones. So you can just check these cases, and then you just answer the question as best you can. The question might not always necessarily say something like this, but yeah, cool. And I think question. Cool. Okay. I think based on the fact that we're already over time, I think what we might do is we might call it there, guys. There's an optional harder question here that's going to be presented in the slides. So yeah, feel free to like have a look at that if you want. But I think based on the fact that we've gone over time already, we might leave it there. And so we're going to leave it at chapter 5. And it's going to start from cryptography and coding theory on Friday with Gerald. Cool. So I'm going to hang out here for a second and see if there's any questions anyone wants to answer, wants answered. And yeah, otherwise, thanks for joining me. I'm aware that like that's a lot of information spat out in just over 2 hours. Hopefully lots of stuff was familiar to you. Hopefully like lots of stuff you were understanding and following along with, and hopefully able to just extend your knowledge a bit more through this session. And yeah, best of luck for the exam. Best of luck. Yeah, like I said, I'll stay here for a couple more minutes and be able to answer any questions if there are any. But otherwise, yeah, thanks for joining me, guys. Yeah, thanks, Gerald. Let me think about this question earlier. Could we use FLT, as Matthew's put it? Actually, let me just check with Gerald or John. Is it okay if I stay streaming for a little bit and flick through and try and answer questions? Easy, HD, let's go. Let me go. Is this where it was? No, it wasn't here. It was here somewhere. Yeah, it was here. Okay, let's think about this. So some use for Maslow's theorem. Okay, so if we think about it, so what's Fermat's theorem? So we've got A with P is congruent to A mod rule 3. So we're saying A cubed congruent to A, or I think I maybe see a way where this is possible. Whenever you're ready to finish, you can stop streaming your own. Okay, cool. Thanks, Gerald. Is Matthew still there as well? Because it looks like if I figure out this question, he's not even there. Congruent to this, which means that we have show that it's always composite. Raise both sides to the power of n. Yeah, because I get what you're saying though, because if you do that, but then I think, isn't that then 2n? And that's 1 to the n, it's still 1. But it's showing that it's composite, because I think I wrote the power wrong here. I did work it out on paper, but I think that's actually something else. But it's the reason I split it is then because then you can show that one of them has to be 1, and then when it has to be 1, that provides a contradiction. Oh no, sorry, you show that you don't want it to be 1, and then when you're doing that, you get a contradiction and say, well, it has to be. So then you get a composite thing. It's an interesting point, because I think I kind of see maybe why Matthew thought about it, in terms of like, because if I look at this expression here, like A to the power of 2 then has to be congruent to 1 mod 3, I can kind of see how we can delve into the realm of this. I can kind of see that, but I don't necessarily see how to prove that you always get a composite. But maybe it's possible. I'm not going to be closed to the idea it's not. But yeah, it seems like Matthew might not be around, and it doesn't seem like there's any other questions. So yeah, maybe we'll end it there. If there's any last minute questions, quickly speak now, or forever hold your peace. Otherwise we'll call it there. Two congruent to 0 mod 3. Yep, I get that. Yep, 2 is the fastest to show that 2. I see what you're saying. So you use the initial thing where you like figure out that it's a multiple of 3. So that's how you get it congruent to 0 mod 3. So you use that initial bit of working, and then you rearrange into that form to then apply it. Yeah, I see what you're saying. So this suffices to show that two to the n is equal to is congruent to 2 mod 3. it's still how do you adjust that composite bit? Because here we say that it has to be equal to 3 times k, so it's like some multiple of 3, and the only way it can be prime is if k is 1. That's the only way that we can say that this is not a composite number there, because we proved that it's divisible by 3. And then I'm unsure how to get this secondary part of the composite into that proof. Anyway, Gerald and I can discuss this in our own time. We can send some messages back and forth to figure this out. I'll spare everyone else watching this on the recording. Alright, cool. Wait,